Hello, Interspeech 2020. I'm Shangyi Zhang from Academia Sinica. I'm glad to introduce you a Lite Audio-Visual Speech Enhancement System, the proposed LavSE system. Here's the outline of my presentation today. The QR code will lead you to the LavSE repository on GitHub. First, I'm going to briefly talk about speech enhancement, abbreviated as SE. The goal of SE is to improve speech quality and intelligibility by converting low-quality speech into high-quality speech. It has been widely used in the front-end processing of speech-related applications. For example, automatic speech recognition, assistive hearing technologies, and speaker recognition. Recently, deep learning models have been extensively used as fundamental units in the SE field. The advantages of deep learning models include their outstanding nonlinear mapping properties and their ability to fuse multimodal data. In research on SE, visual information has been adopted as auxiliary information to facilitate better SE performance, and we call it AudioVisual SE, termed as AVSE. AVSE systems have been proven to provide improved enhancement capabilities compared to audio-only SE systems. However, AVSE implementation is difficult for practical applications because of the additional processing costs for visual input and the privacy problems of face or lip images. To solve these two problems, we propose LavSE, a Lite AVSE system. LavSE includes two visual data compression techniques, an autoencoder-based compression network and a quantization data compression scheme. The former can significantly reduce the size of the visual input while extracting highly informative visual information, and the latter is applied to further reduce the bits of the extracted representation. The experimental results indicate that the proposed LavSE system can yield better performance than an audio-only SE baseline. Moreover, it is confirmed that the user identity can be removed from the compressed visual data, thereby addressing the privacy problem. The architecture of the LavSE system is based on the multimodal deep convolutional neural networks, AVDCNN. AVDCNN receives noisy audio and lip images as the input and generates enhanced audio and lip images as the output. With specific weights, the combination of audio loss and visual loss is used as the final loss to optimize the AVSE model. In the LavSE system, a bitwise data compression technique is implemented. The single precision floating point format is a data format widely used to represent 32-bit floating point variables. The 32 bits consist of 1 sign bit, 8 exponential bits, and 23 mantissa bits. The sign bit indicates whether the value represented is positive or negative. The exponential bits determine the representation range of the value, and the mantissa bits account for the significant figures. Because quantization on the mantissa bits does not change the represented value itself, but only reduces the precision, we drop all the mantissa bits to the exponent-only floating point format, termed EOFP, as our data compression format. In this section, we are going to introduce the architecture of the proposed LavSE system and the two modules for reducing the amount of visual data. The LavSE system includes three parts: data preprocessing, SE model, and data reconstruction. The two green solid blocks outline the proposed visual data compression modules. Encoder AE reduces the dimension of the visual data, whereas Qual Lantern conducts the EOFP quantization. We adopt the log 1p magnitude spectrum as the audio input and the compressed lip feature as the visual input for the SE model. Encoder AE is the encoder part of a pre-trained self-learning autoencoder. The autoencoder consists of 3 2D convolutional layers as the encoder and 3 2D transposed convolutional layer as the decoder. It uses a bottleneck to effectively reduce the size of the visual input to 16.67%. Next, quant length can further reduce the number of bits for each feature element. In this study, we empirically determined to adopt the 4-bit EOFP format, which contains a sign bit and 3 exponential bits. The size of the 4-bit EOFP data is only 12.5% of that of the 32-bit floating point data. After applying the two modules, user identity is removed from the compressed visual data. We used the TMSB dataset to conduct the experiments in this study. The TMSB dataset contains speech utterances from 18 speakers, each providing 320 utterances. We mismatched the settings in the training set and the testing set. The training set consists of the first to 200 utterances from 4 males and 4 females. These utterances were corrupted by 100 types of noise at 5 SMRs. The testing set consists of the 201st to 320th utterance from 1 male and 1 female, corrupted by 6 kinds of noise type at 4 SMRs to simulate a car driving scenario. The leaf or phase image controls used in the experiments were positioned using D-leaf, and we used two metrics to evaluate the SE performance, PESQ for speech quality and STY for intelligibility. We want to first examine whether the incorporation of visual information helps improve SE performance. LavSE AE is our proposed LavSC system with the AE compression module. The baselines include an audio-only SE system and some AVSE systems with different visual features. We have compared 3 different kinds of visual features with our AE compressed feature. They are phase features extracted by VGG phase, raw phase images, and raw leaf images. Table 1 shows the average scores of the above systems with the noisy speech listed on the top for comparison. The results indicate that audio-only AVSE leaf and LavSE AE can notably improve PESQ and STOI. However, AVSE VGG phase and AVSE phase cannot yield further improvements compared to the audio-only system, implying that the entire phase images may contain redundant information that does not directly benefit the SE task. It is also noted that LavSE AE outperforms audio-only and AVSE leaf in terms of both PESQ and STOI, suggesting the positive effect of incorporating compressed visual leaf information into the SE system. Next, we want to further investigate the effects of the two compression modules, Encoder AE and quant length. Their compression ratios are 6 and 8 respectively, resulting in an overall compression ratio of 48. LavSE AE plus EOFP stands for our proposed LavSC system with the two compression modules. Its average PESQ and STOI listed here tell us that even with such significant data compression, LavSE AE plus EOFP can still yield satisfactory SE performance, which is comparable to that of the best AVSE systems, and notably better than that of the audio-only system. Moreover, Figure 7 shows that the performance is robust over different SNRs. In conclusion, the contributions of this study are threefold. First, we verified the effectiveness of incorporating visual information into SE. Second, we confirmed that even if the visual data is significantly reduced, it can still provide significant complementary information for the SE task. Third, using the Encoder AE and quant length modules together, privacy problems may be addressed as well. We expect that the findings in this study will be helpful for implementing the DL-based AVSE model in real-world applications. These are the references of the slides. This is Interspeech 2020. I'm Shangyi Zhuang from Academia Sinica, and the title of this paper is Lite Audio-Visual Speech Enhancement. Thank you.